Okay, in this lecture we're continuing with Dalton's law of partial pressures, and we're going to look at some applications to the problems. We learned from the previous lecture that Dalton's law of partial pressure is an application of Avogadro's hypothesis. Okay, simply stated, if you have gases under the same temperature and pressure, therefore they're going to behave very similar, and therefore their pressures will be proportionate to how many particles or how much you have. Any case, the best thing to do here is to draw yourself a diagram. We've got a diagram, and I've got some gases. I've got 10 liters of hydrogen. Okay, let's do that. 10 liters of hydrogen. I'm just going to draw. Now, of course, in truth, hydrogen doesn't stay in one area. I'm just showing you that the proportions here. We have 5 liters, let's say, of nitrogen. Not drawing the scale, but do the best I can. 5 liters of helium. Okay, party people. So these are the proportions. Again, there's no real boundary here. These gases are able to fly through the entire container. But knowing the proportions of the volume, don't we really know the proportions of the particles because of Avogadro's hypothesis? Yes. Okay. Hydrogen has twice the volume of nitrogen and helium in the same condition, so there must be twice the number of particles of hydrogen. So we can start making some very simple deductions here. All right, so what's the partial pressure of hydrogen? Knowing hydrogen is 400 torr, okay? So knowing hydrogen is 400 torr, we can make some deductions about the helium. Well, helium has half the amount of gas as hydrogen. Oh, here's helium. So therefore should have the pressure. So this should have 200 torr. And that's why this answer is 200 torr. Whoa. Regent's land. This land is your land. All right, any case, what is the partial pressure of nitrogen? Well, because nitrogen and helium have the same volume in this container, the same amount, they must have the same number of particles. So they must have the same pressure. Okay, this is revolutionary. Okay, total pressure in a flask has to equal the individual partial pressures, as we learn. Total pressure equals the partial pressure of, let's say, the hydrogen plus the partial pressure of the nitrogen and plus the partial pressure of the helium. So obviously the total pressure, okay, is 400 plus 200 plus 200, and of course we get 800 torr. Okay, so we were using volumes were proportionate to pressure. Why? Equal volumes, equal number of molecules. Twice the volume, twice the number of particles, twice the pressure. Okay, you can see those fractional and proportionate values in Dalton's law because of Avogadro's hypothesis. Let's move on. Now let's say that there's 5 moles of nitrogen. Okay, changing the problem here. I know that it reads something else, but let's just say we have 5 moles of nitrogen. Okay, so let's go to a new ink. Okay, and let's go to black. So let's say we have 5 moles of nitrogen. So in here, there's 5 moles. Well, if there's 5 moles of nitrogen, how many moles is there in 5 liters of helium gas? Well, that's pretty simple. If they have the same volume under the same conditions of temperature and pressure, they have the same number of stuff. So there's 5 moles of helium. Whoa, revolutionary. And what about the hydrogen? There's 10 liters of hydrogen. There's twice the volume in this container. So there's twice the number of particles under the same set of conditions. So there's twice the moles. Okay, so we would say this is 10 moles, right? Double the volume, double the number of molecules. Because they're in a container, they're under the same conditions. So of course, that is 10 moles. That's 10 moles. Total number of moles is 20 moles. Now let's stop here for a second. Let's look at our fractions that we could have used. If there are a total of 20 moles, and we deal with the mole fraction, let's say, of helium. The part of helium is 5 moles. So let's look at this for a second. 5 divided by 20 equals 0.25. What is this? This is called the mole fraction, big X is for mole fraction, of, let's say, helium, and it's equal to 0.25. Notice there's no units because the moles cancel. It's dimensionless unit. So what does that mean? The mole fraction of helium is 0.25. That means a quarter of all the particles in this container is due to the helium. Therefore, a quarter of all the pressure is due to the helium. Notice 200 is a quarter of the 800 total. So if you wanted to do a real Dalton's law partial pressure question, take this mole fraction for helium and times it by the total. For instance, we would take the total pressure times the mole fraction of the helium would give us the partial pressure of the helium. For instance, the total pressure is 800 torr, as we talked about, times 0.25, which is the mole fraction, and a quarter times 800, okay, is 200 torr. Okay, so any case, don't know why it's going dim and dark on me, but that's the way it goes. Any case, that's what we do here. So number 2, moving on. A container has 1 liter of oxygen gas, 3 liters of hydrogen gas, and 1 liter of nitrogen gas at pressure of 1 atm. What's the partial pressure? So draw yourself a container. Probably draw yourself a better container. And we have a liter, okay, of oxygen gas, that's O2. We have 3 liters of hydrogen gas. Notice I draw it another 2/3 here. Okay, 3 liters of hydrogen gas, which is diatomic, and a liter of nitrogen. So there's my proportionate ratios here, okay, in terms of volume, okay? Now, there's a total of how many liters? Okay, well, if this is 1, and this is 3, there's 5 liters. Okay, what's the partial pressure due to nitrogen gas? Now, I can do a mole fraction, but I can do a volume fraction. Isn't volume proportionate to moles here if the conditions of temperature and pressure are equal? If you say yes, I say yes, we all say yes. Of course, volume is equal to moles times that constant. What's constant? Okay, Avogadro's law takes us back 2 weeks ago. What's constant is temperature and pressure for all these gases. They're in the same container. Now I'm drawing these dividers, but they don't exist. Okay, so let's do a volume fraction. Okay, so a volume fraction would be, now we don't actually call it, there is no value, but the fraction is what? It's for, what's the pressure of nitrogen gas? It's 1 out of 5, isn't it? 1 part over 5, which is equal to 0.2 times the total pressure. The total pressure is 1 atm. Look at that. 20% of all the volume, which really means 20% of all the moles, isn't it? Volume and moles are proportionate, times the total pressure. So what's 20% of 1 atmosphere? Well, that's going to equal 0.2 atms. It's just that simple. So this one is 0.2 atms, this one is 0.2. Gosh, that gives you 4. This has to be 6 for the whole thing, 0.6 I should say, to give you a total of 1 atm. Individual partial pressure is equal to total. 0.6 plus 0.2 plus 0.2, total of 1. That's the answer, 0.2 for nitrogen. Just that simple. Okay, moving on. A mixture of gas is 50%. That would give you a mole fraction of 0.5, wouldn't it? For oxygen molecules. Okay, and a mole fraction for carbon dioxide would be 0.5 as well. Okay, total pressure is 750. What's the partial pressure of the oxygen gas? What's 50% of 750? Okay, all right, 325. Or 0.5 times the total, 750. Why does that work? Mole fraction times the total pressure gives you the fraction of the pressure remaining due to the gas. So that would be the answer. Very, very easy. Okay, 4 and 5 you can do on your own. Okay, and let's go take a gander at, this is pretty simple stuff. Take a gander at your other homework ditto. Okay, so we're doing 1 and we're doing 3. Okay, let me set these up for you. A sealed flask contains 3 liters of hydrogen, 2 liters of CO2, and an unknown volume of Cl2. What do you think you're going to do? Yes, you're going to draw. I've got 3 liters of 3, so we got 3, let's say, liters, 2 liters, and an unknown volume of Cl2. So 3 liters of hydrogen, 2 liters of CO2. This should be an L. Okay. The entire flask is at STP. So that means your pressure total is equal to 1 atmosphere or 760 torr. It doesn't really matter. Okay. The partial pressure of the carbon dioxide is 200 torr. Since they're giving me that in torr, I'm going to use 760 torr as my total. Okay, so what am I going to do here? Well, they're saying the carbon dioxide is 200 torr. That's its partial pressure. Okay. Now look at this for a second. 3 liters. How is 3 liters different from 2 liters? Isn't that 1.5 times more volume? So shouldn't hydrogen be 1.5 times larger? And you get a total pressure there. Now you can think with me, okay, in terms of liters, okay? But I'm going to leave that alone. So we have torr here, you know, total pressure. We know pressure total is going to have to equal to the partial pressure of the hydrogen plus the partial pressure of the CO2 plus the partial pressure of the Cl2. I'm running out of space. Okay, so we have this guy, CO2, and the H2 we can actually figure out from the other one because it's 1.5 times more volume. So you're going to have these two values. You're going to know the total torr is here. You can figure out the, partial pressure due to what's left over. Now, but they don't ask for partial pressure, they ask for the volume of the chlorine gas. Okay, and I'm going to leave that for your own thinking. Okay, but you can definitely get the pressure, okay, from what I just talked about, and then think of the volume. All right, now number 3, I'm giving you, again, a container. Oops, edit, undo. In this container, in number 3, you have grams of 3 different gases. You have N2, you have H2 mixed, and you have NH3 mixed. Grams, you have the amount of grams. Now, grams isn't a how many number. Okay, you know the total pressure, PT, is equal to 2.35. How do I get the individual partial pressures of each of these individual gases just knowing the grams? What do you think I have to convert to convert this from a how heavy number to a how many? Well, you said it. You got to go to moles. And once you have moles, then you're going to have some mole fraction, which we were using before. And once you have the mole fraction of each, you know the fraction of the moles of each, you know the total pressure, you should be able to get the individual pressure. Good luck. See you tomorrow.